All right, ladies and gentlemen, it's after 3 p.m., so it is my pleasure to welcome you to room E2. If you have any questions during the lecture, the presentation, please send them to slido.com with the appropriate hashtag, and all your questions will be answered, I'm sure. So without further ado, it is my pleasure to welcome Daniel Stenberg, and take it away, please.
Hey. Yeah, I'm Daniel. I work for Mozilla. I do Firefox networking during my days. I've been working with curl for 20 years, and I've been doing protocols, HTTP and stuff in the IETF for 8-9 years or so. So today I have a trouble to come up with nifty topics or subjects for talks, so I call it HTTP2, but I really intend to talk a little bit about HTTP1, what HTTP1 is, some of the problems, why HTTP2 was made, and how we made HTTP QUIC, or what is to become QUIC, maybe one day. So I'm going to try to talk a little bit quick and fast, and you can just add your questions, and we can have a lovely, more focused session after this talk. OK, so we had HTTP1 since forever, right? And over the last years, or 5 or so, well, this slide isn't exactly brand new, but anyway, this is how the sort of the trend goes. This is number of objects per average on a website of Alexa top 100,000 or so. The number of objects per website increases all the time. It's probably way higher than 100 now too. And the amount of data for an average website you need to download also increases all the time. More data, more objects. And in fact, if you're checking one of these average websites, you see that more than half of the objects come from the same website, or the same domain at least. Just some facts. And at the same time, HTTP1 is a round-trip bonanza. Ping pong, you know, the site is, this is me, and that's the site, you know, the cloud. And this is time. And you know, when we're asking something from this server over there, and we ask it, and we wait until a response comes back, maybe HTML. Oh, we want the image too, and we want the CSS or whatever. And we ask again, we wait for the answer, it comes back, and we ask again, and the answer comes back. Ping pong, ping pong. And that is potentially a long time away, many 100 milliseconds, or sometimes even worse. So, OK. We have this ping pong problem with HTTP1. So what do? Well, we do many of these, right? So we sort of compensate over time by having many connections instead of just one ping pong. So we can do ping pong over, your regular browser today uses 6 connections to each host name. But OK, 6 connections, that makes, you have to do this over 6 connections. So you instead introduce the head of line blocking problem. You know, this is, each line here is one TCP connection, right? It's like the line in your grocery store. Which line do you pick? Which is the fastest one, you know? Which isn't the one with the trainee behind the cashier? You don't really know. It's really hard to pick the right line. It's always the wrong line. And we have that same problem in HTTP, because we need to pick a connection to send the request out on, hopefully the fastest one. It's a problem. These are some of the problems that HTTP1 has. But of course, we're all creative, nifty. We try to find workarounds around these issues. So we introduce fun things such as spriting. Why ask for 200 images when we can ask for 1 image that contains every single flag in the world at once, right? So instead of doing ping pong, ping pong, ping pong 200 times or 5 times, we do 1 ping and a huge pong, and we have all the flags at once. Of course, that's a sort of, we don't have to do many ping pongs. We get a lot of flags at once. Maybe we only want to use 5 of these or 3, but sure, we got a lot of them. And that's not really good for caching, right? And we waste a lot of data, but we save round trips. Or if you don't want to do it like that, you put the image in your style sheet, right? A huge blob, base 64 encoded. Really nice. It's really hard to see, and you need tools to do this. And again, You ask for the style sheet, and you get a whole busload of images back embedded in there. So you save round trips, you waste data, and it's a bit complicated to generate this. It's really not readable either. But of course, and then if you don't use images, you use JavaScript instead, and then you, boom, make all the JavaScripts in one file, right? For the same reason there. One request, a huge response, but you don't have to do the ping pong. You don't lose a lot of time by doing many ping pongs. So, okay, that's how you do it in HTTP 1. And when there are times that you think that, well, maybe 6 connections isn't really that good either, right? You want more because you have many more objects, many hundreds of images on your web page. So you invent a lot of host names for your site. I mean, this is the same site, but you just come up with many host names because you get 6 connections to each host name. So this is 49 or 56 connections or whatever it is. That's a sort of a workaround. This is a Swedish tabloid, but all major sites these days do it like this if you have many images. Right, so those were sort of funny ways to make HTTP 1 not as bad. You don't suffer as much from the ping pong when you do it like this. But anyway, back in the days, people, of course, realized that this is the way, this is the state of things, so we need to fix this. So this guy was introduced, the HTTP 2 man. Unfortunately, he's only my guy. He didn't take off for real. But, with HTTP 2 then, as the follow-up to HTTP 1, we try to maintain the HTTP semantics, but change how we transport everything. We still do request, response. We still have headers and body. And basically, everything is sort of seen from the surface or from a little distance. It's the same thing. But it is an important step in networking with HTTP because we sort of change how we transport things while keeping the semantics. So the perhaps most important thing with HTTP 2 then compared to HTTP 1 is that we introduce multiplexing. So this train, let's call it the Justin train, and the IKEA train, these are 2 images, of course. We want to send them from the server to the client, and we use multiplexing so we can just send them over the same connection, so they're multiplexed. Just in IKEA, just in IKEA. Many frames over the same connection, and in the other end, we split them up again. This then, of course, has the upside that going back to my surfing ping pong here, me and the cloud, time. So instead then of the former thing, when we did ping pong, we could do it, ask for something. Yes, we wait for a response. We still have these, the distance to the server. It didn't shrink in the meantime. The speed of light is still the same. But we don't have to wait. We can just send another request on the same connection. And the response can come back, sort of interleaved, perhaps like that. And we can ask again. And the responses can sort of come back whenever the server can send it. And it doesn't even have to, the third response here is faster returned than the second response, since they're multiplexed over the same connection. This is perhaps the primary thing we did in HTTP 2, or I'd say it is. There are a few other things. This was shipped in RFC 7540 2.5 years ago, so it's not totally brand new, but it was also then turned binary because it needed binary anyway, so we could do this multiplexing. So we send a bunch of frames, basically, size and contents. And we introduced header compression, so you can actually compress. I would say that outgoing request, ask for a lot of resources, and they are now compressed, which makes it possible to ask for more resources earlier on in the connection. So you get data back faster. And also this fun thing called server push was introduced, which I'm not going to explain much, but that's basically a way for the server to return data that you never asked for. You get it anyway, as if you asked for it. Still an area for more improvements and research and development, because it hasn't really turned out to be very good yet. Anyway, that's that is what, in a nutshell, what HTTP was meant to fix and how it tried to fix them. Already when RFC 7540 was shipped, I think we had around 42 different implementations. So it was already adopted quite well at that point in time. So looking at it then now, everyone supports it, right? I don't think there is a web server out there with any particular use that don't support HTTP 2. So everyone does it, basically. All the browsers do. Well, they did pretty much already from the beginning. So widespread adoption among implementers. I didn't mention proxies there, but they're coming as well. HA Proxy released H2 support just a week ago. So looking at some stats, in Firefox and in Mozilla, I work for Mozilla, we have anonymous data collection that you can opt into, and then we know we can count out of all HTTP responses, how many have HTTP 2 mentioned in them? 43% of HTTP, which is a fun number, pretty good adoption. And HTTP is then all HTTP responses, while in the browser world, we agreed to only do HTTP 2 over HTTPS. So while this counts all responses, it's actually 70% of all HTTPS responses. And HTTPS is the only way we do HTTP 2. It's basically the only way anyone does HTTP 2. It's not required, but that's another matter. So a lot of HTTP 2 from the browser side. Of course, this is then sort of counted by volume, so all the big players here sort of skew the numbers over this hard. The Facebook, Google, and Twitter, and the big ones. But even looking at the other, and then if you sort of, what do the numbers on the internet show? What do servers actually do? We can see that 1/3 of the Alexa top 10K run HTTP 2, which might not be very impressive, but at least it's growing all the time. And it has doubled among the 10 million sites the last year. So it's at least it grows. It grows. So HTTP 2, been here for a while. How has it played out? Was it really that good? I mean, we had a lot of grand ideas, and we thought we would fix everything here. But we can see, again, going back to Firefox, since that's what I work with, I have numbers for it. So we can just look at some measurements we get in Firefox is how far away is the average user from the average site they're communicating with. You know, what's the round trip time to your server? Me in the cloud, what is the distance? And I'll tell you, it's quite far away sometimes. Look at that. The 95th percentile, they're a second away from the server. And you know, when the ping pong takes a second, and you have many requests, that's a long time waiting for answers. That's the excellent opportunity for HTTP 2 to do something. So since you don't have to wait for the response, you can send a lot of more requests and get the answers back much, much sooner. An excellent, so it is in situations like this where HTTP really excel. And you can also count basically the same thing, but we have a queuing time within the browser, which is basically how long internally, when asking for, we want to ask for resources, we want to get URLs, images, style sheets, and whatever. We put the request in a queue, wait for it to go out over the wire. The queuing time, basically. So we can see then, again there, looking at the end of the table, we're drastically reducing the amount of time that requests are waiting until they can go out. And of course, there can't be any response until the request has gone out. So we need a request out as soon as possible. And we can see that we're drastically reducing the worst case. Those people with really, really crappy connections and far away from the servers. Huge improvements. Seen in another way, you can also say that how large is the share of the requests that are actually waiting a long time, and with a long time being more than 100 milliseconds, we can see that we're drastically also reducing the amount of long waiting with HTTP2. So, some interesting numbers. Basically, that's the long tail of people on the darker corners of the internet where things are not as good as we want them to be. But I'm going to show you a little graph here. It's quite complicated, but we're not going to delve into the details. Here is a graph from a simulated network. This is a test run by Fastly. We can see here, this is basically Firefox and Chrome using HTTP1, HTTP2, 40 milliseconds to the server, 0% packet loss. The red and the blue are the H2 versions, and the orange and the green are the H1 versions. We don't really need to look at it. We can just see that the H2 versions are faster than the H1 versions. And we don't have to hooray that Firefox was faster, but yeah. But if we do the same test, or they did the same test, adding the packet loss, just sort of turning up the knob there a little bit, 2% packet loss, everything changed. So now the red and the blue, they're not winners anymore. The red and the blue turned way over to the right, which meant that they turned much slower. 2% packet loss, HTTP2, not as good anymore as HTTP1. Boring. So why is this? Right, sad face. So, packet loss. We now had 1 connection instead of 6 connections for a typical host, right? So if we lose 1 packet, what happens to everything else? A single dropped packet blocks everything, right? So instead of having 5 other connections that could still continue when we drop 1 packet, everything halts. Not ideal. So just then to sort of remind everyone of networking. IP, TCP, TLS, H2. This is sort of the network stack, right? The trains, just in IKEA. When we drop a packet over here, let's say we drop one IP packet, it sort of blocks everything. They're not aligned. When we lose a packet, everything has to wait until we can resend that packet, put it in the stream again, and everything can continue. That creates a TCP head-of-line blocking that we need to fix, right? If we want to fix this problem, we need to fix the TCP head-of-line blocking. So we basically need a non-blocking TCP, and we want to have TLS, and we want to be sort of TCP2, right? So we need independent packets so that we can drop a packet and make everything else continue. So we need to know when we drop a packet, all the other streams that are not related to the packet we don't have can continue. So all these packets basically need to belong to a particular stream. And we, of course, need to make everything resent and everything like as TCP does, so that it's. And yeah, the obvious solution to this would have been to make either to fix TCP so that it could sort of help us here, or we could introduce another protocol that has streams, basically. In theory, we could, but first, we don't. Fixing TCP takes decades, if it's even possible. Since not only do we have to agree on how to do things, then we have a lot of middle boxes on the internet that ruin things, and then we have kernel implementers everywhere that are not the fastest when it comes to adopting to new things. So introducing something new today, we had, for example, just as a comparison, the spec for TCP Fast Open was made roughly 10 years ago, and just it was only a year ago, I think, when Microsoft implemented support for it. So give or take 10 years from spec to implementation widely in TCP. And then it doesn't really work online anyway because of all the mailboxes that interfere and make life miserable for a lot of people. So no, it doesn't really work. So the concept is instead introduced as it was with QUIC. This is the official QUIC logo from the IETF working group. But anyway, we're again then looking at where we want to maintain HTTP semantics and change how we transport it, how we send the same things, but send it another way. And QUIC, as a way to fix this, is done 2 lines at once. It is a protocol designed to run over UDP and provide end-to-end crypto so that there's privacy and security, and there's no TCP head-of-line blocking. So we can actually drop a packet somewhere, and everything else will continue that are not related to that dropped packet or packages. So the streams are fairly independent, which means that you can actually send the just-in train, you can drop a car in the middle, and the IKEA train can pass it. They're independent. And while doing this, we can also introduce other fun things in a protocol that you want to do. Like these days, we want to have features like zero RTT features, which means that we don't want to have this ping pong all the time. We can actually send data already in the first ping. So we don't even have to do a handshake. If we have communicated with the server already, we can send a lot of data in the first packet to, of course, reduce round trips. More data earlier. And we can basically get all these TCP improvements much faster. And possibly, and hopefully over time, we can actually get some of these fun things that are made in QUIC incorporated into the regular TCP over time. QUIC as a concept or protocol was developed, invented, driven, and has been deployed by Google since several years. So if you run Chrome and you run Chrome against Google services, some of you might, you're probably already using QUIC because they've had it enabled for a long time. And it works. It really works sort of as a seen from the grand perspective. There are a few connections or a few users that can't use it since it's UDP, high-speed UDP. That's not really something that we're not used to that on the internet. Nobody has really ever, if we exclude some RTP streams or whatever, you have not really used high-speed UDP before. And this is actually as successful. So if you look at the internet today, 7% of the internet traffic is QUIC already. And this is actually a number that is, I believe, 6 months old, so it might be a bit higher now too. And this is Google QUIC. I'll get back to why Google QUIC is, why it matters. So basically then, so when you have this protocol stack again, you see how they neatly line up everything here. So when you drop something, it's just that train car. It's just, in this case, the just-in train. We lose that train car, the other train can continue. They're independent. This is the concept of QUIC. And then Google, who made this, they decided that, well, that they wanted to make it a standard. They took their protocol to the IETF and said, hey, we should take it through the procedures and we should make a standard protocol out of this. Fun. So they did, and the process started. The protocol changed quite a lot from what Google brought to the table and what the IETF wants out of it and how it's being made. So the Google QUIC and the IETF QUIC, sort of not the same thing anymore. Oh, I'll get back to that. But anyway, so in comparison then, if we want to see how a protocol stack for the regular HTTP2 as we see today is compared to the QUIC, it basically works like this. The HTTP2 way is, that's HTTP2 over TLS. Usually, you don't actually need TLS if you can still do HTTP2 without it, but this is basically how it works. But instead, if you want to speak QUIC, And this is the IETF QUIC style. It is UDP. So, and then there's a transport QUIC there, made to transport whatever over UDP. And it has streams, and it resends, it has congestion control, and everything. And then you can send HTTP over QUIC. Pretty much the same thing. HTTP, as we know it, sent completely differently over the net. It's not even HTTP 2, really. It's more, we can more look at it as HTTP over QUIC. It's HTTP 2 like. And to upgrade to QUIC, if you do, this is a, right, I should just say it like this. If on the internet today, we have something called URLs, you might have heard of it, and they're all using HTTPS these days, right? So how do we introduce QUIC in this? QUIC running over UDP, that's not TCP on port 443, right? That this is. So how do you kickstart this? How do you start to talk UDP on port 443 instead? So basically, you use it like this. This is the alt services header was introduced in this RFC 7838, which is a way for the server to say, you can also access my services on this other site and port number. It is the same origin, just a different protocol, port, server, whatever. So that's basically what you tell. As a server, you say, oh, I can also do HTTP over QUIC on this port number. So a compliant server, a compliant browser or client would then connect with QUIC on that port number and try to use it. And then sort of transparently switch to that instead of the HTTP 1 or 2 version you used on the other connection. Complicated. No, it's not that complicated. So the IETF QUIC, that the process that started when Google brought this to the IETF, started in 2016, a little over a year ago. It has a massive interest. All the interim meetings we've had so far I think we have more than 50 people attending at every one of them. And it's going to be more than just HTTP2 like. Google made QUIC as a way to send HTTP2 frames over UDP, and they were happy with that. But when they started the work in the IETF, they said, nah, we want to do more than just HTTP. So QUIC is turned into a transport protocol that is going to be able to transport more than just HTTP. DNS being one of the primary things that has been discussed. So there's a QUIC transport layer, and there's a QUIC application layer. Right. There's a fourth interim meeting in Melbourne soon. So there's this IETF version of QUIC that still hasn't been completed. There are internet drafts. They're on number 6 now, I think. Which is a protocol that it differs quite significantly from the Google one. They're not binary compatible. You can't switch between them very easily. Google still runs their Google QUIC in both ends, so there are no live implementations of the IETF QUIC yet in the world. There are 15 implementations listed on the wiki page for QUIC, which I think is quite a large number of implementations of a protocol that is mighty complicated, since you pretty much have to implement your own TCP plus TLS plus HTTP. So a lot of moving parts to make it right. And I think, well, I'm sort of guessing here that we might see some early tests of this early next year. I've done this presentation before, and then I said mid last year. So I guess sort of, I'm an optimist here. It might take much longer than this as well, since there are a lot of strong wills involved in this development. So I can't really tell how long it'll take. Right. So basically, QUIC is not HTTP 3, even if it's, I would say it is HTTP 3 in everything but the name, because this fixes a lot of the problems of the HTTP 2 and without really any downsides. So this is the natural next step for anything HTTP transport like. And it's not TCP 2 either, even if I personally think that's a great name for it. It's just QUIC, even though, as I mentioned here, there are many different versions of QUIC. So just saying QUIC now is really complicated. Which QUIC do you talk about? So just to round everything up then. HTTP 1 has a lot of problems. So HTTP 2 came, multiplexed, binary, and it is everywhere. You can deploy it. And if you deploy it yourself, you'll see that a lot of users, of course, already have it in their client. So if you run your site on HTTP 2, you will see that by far more than 50% of your users will use HTTP 2. And it generally makes your sites faster. And the IETF version of QUIC is certainly coming. And it has support from a wide range of industry players. I mean, not only browsers and servers, but also big server service operators like Facebook and the big ones. So it is coming, and it's we can view it as HTTP over UDP, or HTTPS possibly over UDP. Thank you.
Thank you, Daniel, for a very interesting speech. You certainly gave us a lot of food for thought. And now it's time for questions from the kind audience. The 3 most popular questions are listed on the top. If you would be willing to read them aloud and answer them at your own speed.
Why can't we see speed data for our favorite browser, the IE? I don't even understand the question. But when I present numbers or whatever I talk about here in my slides, I present numbers that are openly available. Anyone and you can go and get and fetch and compare yourself. I don't have any numbers for IE. I can't compare. I haven't run any browsers against browsers here. So, no, sorry. Right, moving on. That's not a question. But thank you. All network nodes proxies need to support HTTP 2 before I can use it, or just my browser and the server. Well, not all. First, of course, you need both a client that speaks HTTP 2 and you need another end that speaks HTTP 2. Both ends that you communicate between both needs to speak HTTP 2. But if you don't, you will keep on talking HTTP 1. Everyone will try to upgrade to HTTP 2 if they can, and they will use HTTP 2 if they can. Otherwise, they will stick to the number 1. So most users, you won't know if you're on HTTP 1 or HTTP 2 when you're using a browser. You will just use whatever works for them, which means that most of you use a browser that can speak HTTP 2, and you talk to servers out there that some of them speak HTTP 2, some of them don't. You don't need to care, and you won't see it anywhere. Well, you can see it if you want to, but so that's basically how it is. And if you're talking through a proxy, the situation is then slightly more complicated. It depends on which proxy we're talking about. But if you're talking about a proxy that you use sort of in your client and to access the internet, we're talking about HTTPS servers here. And when you're talking through your normal client-side proxy, you tunnel through the proxy, basically. And then it doesn't matter what the proxy speaks, really. So you tunnel through the proxy to the remote server so that the remote server needs to support HTTP 2 and your browser, of course. Put simply, at least. So moving on. Can we say that QUIC is HTTP 2 over UDP, or does it come with other improvements too? Well, for us, if we're talking about HTTP users, I think we can say that yes, it is going to provide HTTP 2 features over UDP. It is going to provide a few more, like it fixes the problem with zero RTT, so we can send that first HTTP request, get me the HTML. That can go out much sooner with QUIC than it can with HTTP. But otherwise, it'll be roughly the same. But since QUIC is going to introduce, it's going to be a transport protocol as well, we can also sort of think of a future when we do other things over QUIC than just HTTP. But as a HTTP user, it's going to be a slightly better HTTP too. Can we inspect in Chrome Firefox which protocol we are using for every page? Yes, we can. Just pop up the DevTools and check in the headers and response things. You will see it. I think both Chrome and Firefox insert data there in, at least for HTTP 1, HTTP 2. Since Chrome, I'm not sure how you see QUIC support. I haven't checked, but since we don't have the IETF QUIC yet, so we don't have that in Firefox. I haven't really figured it out. But I'm sure you can see it similarly in Chrome if you just check out the DevTools and see how it looks like. Why not using SCTP as a transport protocol instead of TCP UDP? That's an excellent question. I didn't really delve into that. SCTP is a protocol like next to the TCP and UDP in the protocol stack. So it's basically, it is a multi-streamed protocol that is basically many streams over a single connection. Exactly what I've been talking about here, and exactly what HTTP2 is. But we're in the unfortunate situation that when we do things over the internet today, we all sit in our homes. We have Wi-Fi endpoints, we have routers, and we have the ISPs with routers, firewalls, blah, 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 all the way through the internet. And these machines, they know that everything on the internet is TCP or UDP, period. So when you're trying to introduce a new protocol or use SCTP, which then is a new protocol, it doesn't work. There's a large percentage of all attempted connections for SCTP that will just be blocked, killed, died, never seen on the internet. So this has been tried many times, and basically everyone has given up. There are too many middle boxes on the internet that only understand UDP or TCP or ICMP, but still. So basically we don't see new protocols being even attempted to become deployed on the internet because they're not getting through. So in order to get new protocols to get through all these stupid boxes, we build things on top of TCP or UDP. That's why. There are other sort of minor issues with SCTP that might also make it not really the ideal protocol for this. But anyway, that's the primary reason is that it's really, really hard to get it through. Is QUIC a binary protocol as HTTP2 or plain text as HTTP1? It is binary and it is encrypted by default end-to-end. So there is no plain text version of QUIC. There is a plain text version of HTTP2, but for QUIC, it is TLS 1.3, nothing else. In QUIC, is there a way to prioritize wait one stream over the other? Yes. In the train case, then IKEA just-in train, exactly as you do in HTTP2, you can say, well, I want to have the just-in train. That's much more important than the IKEA train. And in HTTP2, as in you will be able to do in QUIC, you can basically say that one train is even depending on the other train. So you can say, send me the entire train first, and then the other train, if you want to. Or you can just say that this is twice as important as the other train. And the server is then supposed to use that as a hint if it has a choice. I mean, if the server is idle anyway, it'll just send whatever it has to do. But if there's a race, it'll use the weight or priorities as a hint of how to do it. That's already in place in HTTP2. So, add more questions. Do you think other TCP protocols might eventually move from TCP to a QUIC UDP trick, so-called TCP2? Yes, I think QUIC as a transport is going to be provided now and available to browsers as in the first step. So I think it is going to be very tempting for them, for everyone to add things on top of QUIC, since and you already have the stack there. It's easy. It's already encrypted, private. It works. You have streams. You have flow control. You have congestion control. Yes, so I think it's going to be very tempting. And as I said, DNS is already being discussed, and there are many other things. And you can also imagine other transport-related things to be added, like multipath or even connection with like UDP-like connections over QUIC, so that you won't have to retransmit, for example, if you lose packets. How do you deal with packet loss in QUIC? Pretty much, it's not entirely written in stone yet, but packet loss in QUIC is basically done the same way you do it with modern TCP. That said, the congestion control part of QUIC is not really finalized. So there might be different congestion control than your ordinary TCP uses. But otherwise, it's roughly the same, I would say.
All right, so that was the last of the questions. If you want to join Daniel and talk more about technology and delve deeper into the issues, you can join him in the speaker's corner on the corridor. Thank you very much and see you there.
Thank you.